Gang, this will be the final video in lesson 6. The title kind of tells the story, what happens when things go wrong. I think as most of you know, I've advised a lot of doctoral and master's level students on their theses, and I've taught statistics to a whole lot of people at Shawnee State and actually some other universities as well. And one thing that they always kind of get frustrated with me is we deal with these data sets from textbooks, and there's no missing data, and the assumptions for the most part are all met, and we report the information, and this life is just perfect. Well, when you start dealing with raw data, real life data that you've collected, you find that all kinds of things go wacky. Even in a year-long statistics class, I can't cover all the things that can go wrong and the solutions to everything. You just kind of have to have these ideas that things can and probably will go wrong with real-life data, and just investigate ways to get to solve those. Sometimes you have to reach out to a statistician and say, this is what I got. How do I take care of it? I thought it was only, just being completely transparent with you, I thought it was good to maybe run through an example where things just start out with well-intended goals, a research statement, and they just go absolutely bonkers. And what would I do if this happened? So the illustration that we have here is our weight, HDL, and waist statistically significant predictors of BMI. So, as you might imagine, I want to run my model first. So I'm predicting BMI from weight and HDL and waist. All right. So I can run the summary of my model and see that things look kind of cool starting out. No major deals. Waist is statistically significant at the 0.001 level. HDL is statistically significant at the 0.01 level. And weight is statistically significant at the 0.001 level. Our model diagnostic has a high F value, which means it's going to have a low P value. Degrees of freedom 3 and 296. So as a set of predictors, weight, HDL, and waist do a good job of predicting a person's BMI. All right, so life is all good, right? And we report the means and standard deviations, as we should know how to do now in our sleep. The problem is we run into some major concerns. So let me access the library for CAR. And again, if you haven't installed that, you need to before you can access the library. And I run the Shapiro test on the model residuals. And I get statistically significant result, which tells me that I have a concern with normality. I also, and I'm not going to do it over here because I've done it in previous videos, also ran a QQ plot. You can see that there are a slew of data points outside this confidence band. So I have even further concerns with normality. Equal variance assumption, I don't have a lot of concerns because the variances as I go across seem to be pretty equally distributed across each level for X. And it kind of looks like a shotgun blast, maybe a little bit too much clustered right here, but yeah, I have no concerns with the equal variance. Now let's get into the test of independence, the Durbin-Watson test, and see what, for the model, and you can see that we get a statistically significant test at the 0.001 level. Our Durbin-Watson statistic is extremely low. We have major issues with autocorrelation. I should say independence was verified with a major concern for autocorrelation. Again, no real concerns with equal variance. When I run my VIFs, remember for VIFs, it's the variance inflation factor. And those, if the red flag is if any of them are above 5. And I run the VIFs for my model, and weight and waste emerge higher than I said 0.05. It should be 5.00. My bad. So let me restate that. If our VIFs for any of our predictors is larger than 5, then we have concerns with multicollinearity. Now, so what that tells me is 2 variables, most likely weight and waste, are so highly correlated that they're tinkering with the mathematics, the calculations behind the scene that calculate these regression coefficient estimates up here. And that's a problem. That's something that we need to address and needs to be resolved. Now, if you go on down, you can see that I've reported the results, but you can also see that the correlation between waste and weight is not only statistically significant, but it's almost 0.90. That's an extremely high correlation. So what this is telling me now is that waste and weight are so highly correlated that not only are they causing these mathematical issues behind the scenes in these calculations, but one of them needs to be deleted. So what I do, and I don't even know if this is the right approach or not, but this is what I was taught in the way that I proceed, is I go ahead and run the model and of weight and waste, which one has the highest t-value? Will waste. So I'm going to delete weight and rerun my model. So I'm just going to, let me see, I'm going to go up and get it. And I'm just going to call this model 1. And I am going to delete weight. And I'm just going to go ahead and run the summary for model 1 and see what happens. Well, I have statistically significant predictors. HDL and waste are both statistically significant. My model, the set of predictors are statistically significant. I'm explaining an impressive 84% of the variance in Y by these set of predictors being in our model. So let's take a look at what concerned us previously. So I'm going to go up, grab the Durbin-Watson test, but I need to run that on model 1 now. And you can see we still have extremely small. So we have a concern with independence here. When I go back up and run my VIFs for model 1, notice that both VIFs kind of level out. They're both below 5, so I have no concerns with multicollinearity. At this stage, I would have a really important decision to make. Do I just proceed and try to find a different model? One thing I may do is maybe I want to dichotomize. I'm trying to predict BMI here. Maybe I should dichotomize BMI in terms of high and low and use a logistic regression model where I'm not going to run into these kinds of issues. Maybe I just scrap the model and try to find another way to describe the relationship. But right now, this is concerning, and it would be really difficult for me to proceed with this model. But if I did, I would definitely proceed with just waste, and I would not include weight. So I know students hate this because students like when you're learning something, you don't want all these caveats thrown in and you don't have clear answers. But this is a complicated design. I honestly don't know what I would do. I think most likely I would probably delete weight and report that the independence assumption is violated and we have problems with normality. And report the values and let the reader decide on their own if this is a worthy analysis. But anyway, welcome to my world. If it only went always perfectly, it would be super cool. But again, it doesn't. So, all right, that's all I got. Take care.